So, very good afternoon, everyone who have joined for this interactive session. Uh, this is the second interactive session for the NPTEL course Experimental Physics 2, which is being taught by Professor Amal Kumar Das from IIT Kharagpur. And I am Rinalini, Research Scholar from School of Physics, University of Hyderabad. And as you know, this course has three modules. The first one was dealing with another set of experiments regarding electricity mechanics and other such topics. This experimental physics 2 module is basically dealing with optics and quantum mechanics related experiments. But this first 2 weeks we'll be talking about discussing about the basics that knowledge we should have when we are working in any experimental lab. So like first week, that is the last week, we discussed basically we summarized other things, but yeah, we majorly discussed about error analysis, right? How we should whenever we take measurements, they are error related to it, and how we should deal with. So yeah, so last week uh, we discussed about error analysis, and there on the NPTEL website, if you will see, there is a book suggested for this particular concept. This is the this is the screenshot of that sorry cover of that book. You can refer to this book, or I would suggest, because I have gone through this NCERT class physics textbook, in which depending on the version of the book, the chapter 1 or 2 deals with units and measurement. So this book I think is very good. It's concise form it is to read about error analysis that we discussed last week, and about significant figures, concept of significant figures, that we are going to discuss in today's class. So both these topics is covered very nicely in this chapter as well. So this is the book I'll suggest for these two topics. So last time we had discussed about accuracy and precision in any measurement. We had understood using example that what do we mean when we say a measurement is more accurate or precise, or both. After this we discussed error analysis, how errors are added or their product. Then these were the summaries of experimental physics 1. The experiments we had discussed under module 1, because mostly your assignment, I think, which is due on 5th of February, that had questions more from error analysis and oscillations or simple harmonic motion related. That's why I focused more on oscillations, and related questions on this we had done, right? So let's start this week's. So in this week, we'll get introduced to the optical components somewhat, but mostly again, as I went through your assignments, I see more questions on again error analysis and significant figures. So first we'll understand what are significant figures and how to how to consider them when we are adding or doing any arithmetic with any measured value. So we'll understand that. Then today I've brought a lot of numerical problems to understand error analysis based questions also, and significant figures combined together. Those are mostly from like last year's assignment questions, so they will be definitely useful for you to solve this time's assignment questions. Okay, so let's start our topic, which is significant figures. So what happens, like last time we were talking, whenever we carry out any sort of measurement in any lab, we measure some value, and then there is some error in it depending upon the least count of that instrument, or there are many other reasons that we had discussed earlier. There could be many sources of those errors. So whenever we report value, we want to tell whoever will read that value that what's the reliability of that reported value. There comes the concept of significant figures. Like for example, say uh, for a simple pendulum, we have calculated time period. For example, let's take it's 2.63 seconds is the time period we performed the experiment, and after calculating we are reporting 2.63 seconds. So here what happens, this means this reported value has some certain digits and some uncertain digits. This certain digit is also called certain or reliable digits. So when we report any measured value, it has certain or reliable digits plus uncertain digit. First uncertain digit, because after that uncertain digit there is no point of going to further decimals. So when a reported value has these two parts, we call that number of significant figures. Let's again, so what we mean by significant digits or significant figures is it consists of reliable digits or certain digits and first uncertain digit. It indicates the precision of measurement, which depends on the least count of measuring instrument. Again, it's talk about the error only, but here we only focus on the first uncertain digit. So as I gave example, if time period we are calculating to be 2.63 seconds, so here the significant digits or significant figures is 3. Number of significant digits is 3, because 2.6 is the reliable digit. 2.6 is reliable, and this 10th decimal digit which we are measuring to be 3, this is first uncertain digit, because maybe whatever instrument we used that had least count of 0.01 second, and that's why we calculated or measured the time period to be up to 100th decimal digit. This is 10th, this is 100th decimal digit. So 2.6 are certain digits and this last is the uncertain digit. So totally the time period has 3 significant figures. So okay, let's try to understand it a bit more. And there are many rules that we need to keep in mind. Like this way we had done it for error analysis, what is the resultant when two errors are added or their product or division is taken, the same way we have to keep in mind there's various rules when we are dealing with similar mathematics. So let's discuss these rules. First rule is all the non-zero digits are significant. So this is pretty straightforward, that all non-zero digits are significant, whether it comes before decimal, after decimal, or anywhere. They all are significant. All the zeros between two non-zero digits are significant, no matter where the decimal point is. What this means is, if I did some measurement and I have a number like 30021, then here we said zeros are not significant, but non-zero digits are significant. But if the number I have got, zeros are coming in between non-zero number, then even they are significant. Means if this is some measured value, then here the number of significant figures will be 1, 2, 3, 4, 5. So here 5 significant figures are there. Even here, okay, there was no decimal. Even if the value is like this, or if it is like this, still the number of significant digit will remain same, because the rule is all the zeros between two non-zero digits are significant. Okay, so this is the second rule. We'll see why these rules are so important, because okay, I can give you one example. Like if we are adding or dividing any digits, sometime in calculator we get up to many decimal digits, then how to decide up to where we have to keep? So there it's very important also, because uh, calculator gives us many decimal digits, but the what we say resolution of the instrument, it has some limit. It can only calculate, it can only give till 0.01, maybe its resolution is limited, and we are using a calculator and it's giving decimal digit up to 6 7. So that doesn't make sense, because the instrument can give certain value only till here, it has some limit. So accordingly our result that we are reporting using this instrument, if we are restricting it to two decimal digit, then it makes sense, otherwise it doesn't make sense, because the instrument itself has some limit. So that's why the significant digit and concept of error analysis and these rules are so important when we are reporting any values. So I mean, you can understand that just only performing the experiment carefully is not important, even the way we are reporting it is very important, because it tells about the precision and accuracy of our measurements. Okay, so moving on to the third rule. If the number is less than 1, the zeros on the right of decimal point but to the left of first non-zero digit are not significant. Again, let's understand what this means. If the number is less than 1, then zeros on right of decimal point but to left of first non-zero digit are not significant. This means if a number is like something like this, okay, here the number is less than 1, of course, and the zeros on right of decimal point, these zeros are on right of decimal point and left of first non-zero digit, so these are not significant. All these three zeros are not significant. So if after some measurement this is my answer, then here the significant figures are only, number of significant figures will be only 2. Only these two digits or figures are significant. So this is this third rule. Now the fourth rule is the terminal or trailing zeros in a number without a decimal point are not significant. Here you can see example. If some measurement gives me 123 meters, there is some stick or something which is one, or building 123 meters long, then this number of significant figures here will be 3, right? Because there is no zero, so it's pretty clear. If this is in meters and if I'll write it into centimeter, then it will become 1 2 3 and 00, means 12,300 centimeters it will become. But these are same, right? It's just I'm expressing it once in meters and another times in centimeters, but the value is mathematically same. And even with this rule of significant figures, you can see that the rule says the trailing zeros in a number without decimal point are not significant. So in this case also, even if you change this 123 meter to 12,300 centimeter, the number of significant figures still will remain 3. So this is how you can see that it makes sense. These rules make sense. Just because I am changing it from meters to expressing it from meters to centimeters, the least count or the resolution is not changing of the instrument. So that's why the significance, number of significant digits should also not change. So even if you express it in meter, centimeter or millimeter, the number of significant figures for this particular value will remain 3. So this is the rule that the trailing, that means the last zeros without decimal point, are not significant. The trailing zeros in a number with a decimal point are significant. Now this is another case where if these zeros are coming after decimal point, then they become significant. The reason for this is that, again, as I said, if I have some equipment, instrument to measure, like we in module 1 we had talked about vernier calipers, or if we take our simple scales, 15 centimeter scales that we use, it gives its least count is 1 millimeter, that is 0.1 centimeter. It cannot go less than that. Similar way, vernier caliper we had used, its least count is 0.01 centimeter. So these values cannot go down than this. But using these equipments, if I am measuring some length which is coming out to be 3.5 doubles, not with using vernier caliper, I can go only till 100th decimal, that is up to 2 decimal digit. So if I'm using vernier caliper, I can report a value to 3.50 centimeter. So that's why here the 0 is significant. It could be, maybe if the thickness is more, I will get 3.52 centimeter, then here this is also significant. But if its thickness is little less, maybe I am measuring it to be 3.50 centimeter. So this whole number up to this second decimal digit is significant. That's why after decimal point, because it depends on the resolution of the instrument, that's why if we are reporting a figure, measured quantity this way or this way, then these zeros are significant. So for this number of significant figure will be 4, and for this number of significant figure will be, so these will not be significant, sorry, okay, let me write here, the number is 0.06900. And if you recall, use all these 5 rules that we have discussed till now, you will understand these two are not significant. We discussed this in third rule, but these two zeros are significant, as we discussed in fifth rule. So totally in this reported measured value, number of significant figures will be 4, right? 1, 2, 3, 4. So number of significant figures will be 4 here. Okay. Moving on to next rules, we have 2 more. For a number greater than 1 without any decimal, the trailing zeros are not significant. Okay, I think this is the same one we had earlier, that if a number is more than 1, means if a number is like anything 2 or 250, without any decimal, the trailing zeros are not significant. I think this, no, this is also pretty much same, or the trailing zeros in a number without, I think, yeah, it got repetition or something, but it's the same rule, that if a number is more than 1 and there is no decimal point, then trailing zeros are not significant. So this is how it is. The reason behind this is because even this we can express like this. This is the scientific notation way. So that's why we consider that this number has only 2 significant digits.
Itu pelurahan orang ada tentang gimana ya?
Sorry, if someone is asking doubt, I didn't hear, or otherwise maybe mistakenly you unmuted yourself. Or is someone asking doubt?
Sorry, ma'am.
Okay, so if there is no doubt, I'll continue. So in, like, let me explain this again. If I have a number like this, then number of significant figures are 2, because this trailing or last zero is insignificant. Why? Because in scientific notation we should write in exponents and powers, and when I'll write like this, you can clearly see here number of significant digits or significant figures will be 2. So that's why this rule is there. For a number with a decimal, the trailing zeros are significant. This is again the same, I think we discussed here. If there is decimal point, then trailing zeros are significant. So if I'm writing 2.5, then it becomes 4 significant figures are there. Okay. So together it may look quite confusing, especially all the rules together. So let's do, I think, yeah, okay, there are some rules more about adding and taking product, but after that we'll do many problems today, so that this concept of significant figures and rounding off will become clear to us. Okay, so what happens is when we do arithmetic of these quantities. So as I was saying, say this is one example. We have to calculate density of this material. Mass is given up to four significant figures. We can see here four, all four digits are significant. Volume is given here. You can see it's given up to two decimal digits. Maybe for this weighing balance that we used, its resolution was up to 3 decimal digit. For measuring volume, we used some equipment whose resolution was up to only second decimal digit. So that's why they are different instrument, their resolution or least count will be different. So what we have to consider then when we are calculating density, because density we know we take ratio of mass to volume. So for mass we have four significant figures, for volume we have three significant figures, right? 2, 5, 1. Now, and yeah, so if I'll take ratio of this is the value I'm getting. If I'll use a calculator will give me up to, I don't know, these are, I don't know, 10 or some decimal digits it's giving. But is this the correct way to report this result? So yeah, sorry, it's up to 11 decimal places. But is it the correct way? So what this, as I said, the equipment that we used to measure this mass, it had least count or resolution of up to 3 decimal digit. For volume, the equipment that we are using, it had least count or resolution of up to second decimal digit. So our final answer cannot have this much resolution. When we are reporting a value with up to so many decimal digit, in a way we are trying to say that we measured with this much precision. If you remember the class we had discussed about accuracy and precision, that the value close to the true value we call it more accurate, but if we go get more decimal digits, that means we are talking about very precise value, that whatever we measured it's very precise. So if we are reporting it to up to 11 decimal digits, means I don't know what advanced instrument we have used to get up to 11 decimal places, but that's not the case. If somebody will see that no, what we have used, those equipments didn't have this much accuracy. So that is why this is not the correct way to report our value. Just because we calculator, or even if we manually calculate, we'll get these many digits, but that's not the correct way to scientifically report this. So what we have to consider here is, here comes our rule, that in multiplication or division, the final result should have as many significant figures as there are in the original number. But which original number? We have two numbers here. So the original number with the least significant figures. Here there were four significant figures. Here there were three significant figures. So in our final answer, we should have as many significant figures. This is for the case of multiplication or division only. Okay. So when we are multiplying or dividing such quantities, the final answer should have as many significant figures as are there in the original number with least significant figures. So here one measurement had four significant figures, another measured value had three significant figures, and when we are taking division of these two, our final answer will have three significant figures only. So when I get this from calculator, I have to round off. If you remember what rounding off, I think we all do in day-to-day life, that if the time is say 2:29 p.m., then we round it off and just say it's 2:30 p.m. So we already know the concept of rounding off, but here we have to consider up to what decimal digit we have to do, because yes, it depends. Maybe you can just tell somebody that it's already 3, come fast. So that how much we have to round off in daily life, maybe we don't consider much about it, but when we are talking about experiments, here everything should have a reason. So the rule, as I cleared this, that the least significant figure here has three number of significant digits, so our final answer also will have three significant figures. So how we'll remove this? It's not like I'll just say okay, just remove these many digits, because I have to tell only three significant figures, so I'll write 1.68 gram per centimeter cube and this is my answer. No, we cannot simply remove these remaining decimal numbers. We have to use round off concept and tell the correct as much the value should be as much accurate as it can be. Like here, if you start seeing, if I tell you like from this first step, then if you remember again, there are two rules for rounding off. If a number is less than, okay, let's take example. If I have a number like this and I have to round off this to this decimal place, then if this number is more than 5, then the number before will increase, right? If I have to round it off, it will become 2.6. But if this number is 2.53, since this digit is less than 5, so this will round off and remain 2.5. So this we all know. There is one more rule that says that if this digit that we are talking about, we are saying if it is more than 5, then this will increase. If it's less than 5, it will remain as it is. But what if this last digit is 5 itself? Then what will happen? In that situation, we will increase this number if it's odd. What I mean to say is, I'm trying to round it off to 2 decimal digits. Right now there are 2 decimal digits and I'm trying to round it off to 1 decimal digit. Now here my last digit is 5. Then if my second last digit is an odd number, then I'll increase its value and make it 2.6. But if it is 2.45, then since it is an even number, according to the rule, it will remain 2.4. Same way, if it is 2.35 and I have to round it off, then since it is 5, I'll see if this is odd or even. Since it is odd, after rounding off, it will become 2.4. If it would have been 2 point some other number, 65, this is 5, so I'll check if this number is odd and even. Since it is even, so it will remain 2.6. So these are the rules for rounding off. Okay, now so as I said, we can simply not remove all these numbers and write up to considering 3 significant figures. We need to use round off technique. So here if you see, the density that was calculated was 1.68804780,876. We can do directly also, but just to explain it first, if you look at this, it's 6, so more than 5, so it will change 7, it will increase, right? So it will make it 8. Now 8 is again more than 5, so it will change this to 9. Then 9 is more than 5, so it will change 0 to 1. Now 1 is less than 5, so this 8 will remain as it is. Now next, again we have to round it off, because only till 2 decimal digit we have to consider. So that's why I'm telling 1. We don't need to start, we can directly, I think you guys are already experienced, you can directly see there is a 0 here, so you can simply start from here. But just to make it clear once and for all that this is how it actually works. So here it's 8, so after that, since it is more than 5, this will change to 8. This is 4, it will remain as it will again become 5, and there is 0 here, there is 5 here. As I said, since this is even, it will remain as it is. and since it is 0 which is less than 5, it will remain 8, and because it's 8 which is more than 5, this will change to 9. So our final answer rounded off to mm, a 2 decimal digit will be 1.69 gram per centimeter cube. So we have to consider, keep in mind that this significant figure rule we have to apply, but not simply rejecting other digits, we have to round off it properly. And you can see also, because the value was 1.688, so if we are reporting it after rounding off like this, then it's closer to this, right? But if I simply reject all this and say 1.68, then people may think it's 1.680, or I mean it's 1.68. It's farther from 1.688, right? If you round it off, it will be closer to 1.69. So that's why important that we round it off properly. So I hope because we have combined two concepts here, significant figures and rounding off. So this is actually what goes behind whenever we measure and report any value. Maybe it got too much maths here, but let's do some more examples, and it will come naturally. We'll be able to understand that we should not just report the value as it is. There is some rule behind it, how we should be reporting. So this was the rule for arithmetic operation for multiplication and division. Let's see what happens when we are adding or subtracting two quantities. So here we have three weights of, I don't know, maybe some different kind of fruits or some chemical we have. So the weights here is, let me write it like this, 436.32. These are in grams. Another weight is 227.2 gram. It's only up to first decimal digit. Third is 0.301. These are different weights, and I think the equipment that has been used to weigh them also has different resolution, right? This first one could give up to 2 decimal digit, but this another weighing machine could only give up to first decimal digit, and this one is with even better resolution. It could give the weight up to 3 decimal digit. So these are three different, I mean these numbers are with different resolution. So what rule we have to apply here if I want to find out the sum of all this? So if I simply add it, what I'll get is there is nothing. So when there is nothing, usually in maths, to fill the space we put zeros everywhere, right? Because in addition it doesn't make any issue. So here we can see if I add, will be like this. There's 6, 7, 8. This will be 13, 4, 5, 6. This will be 6 again. So simply doing the math. Okay, again I'm sorry, somebody's mic is on. Please mute it. So simply by doing the maths, I'll get the value like this. But again, we have to keep in mind about the concept of significant figures. So how should we round it off? For addition, the rule says that in addition or subtraction, the final result should retain as many decimal places as are there in the number with least decimal places. What we want to say is that my final result, the number of decimal places in my final result, like here the number of decimal places, we are not talking about significant figures here, be careful. For addition and subtraction, the rule talks about number of decimal places. In multiplication and division, we were talking about number of significant figures, but in addition and subtraction, we are talking about number of decimal places. So in this, we have, Is someone asking doubt? I'm sorry. I don't know. It's reading. Okay. So here the number of decimal digits are 2. Here the number of decimal digit is 1. Here the number of decimal digit is 3. So we have to consider here the number of least decimal place. So least decimal place is 1. We have a quantity with 1 decimal digit. So in my final answer also, the I should report it with like this, the least decimal place. If this would be up to 2 decimal digit, say 227.22, then of course I'll add whatever it will become, okay, and in my final answer can have 2 decimal digits. In that case it can have 2 decimal digits, but since we have one quantity with 1 decimal digit, I mean there is one quantity with 2 decimal digit, there is another quantity with 3 decimal digit, but we have to consider for our final answer that how uh, the least decimal digit that we have added. So here we had a quantity with only 1 decimal digit, so our final answer also will have this. I showed for change. Our final answer also will have up to only single decimal digit. So these are the two rules for this. Now let's do the first question. This is related to rounding off. We have to round off this number, which is 0.583, to the nearest tenth. Now, if just to clarify, because sometimes we make mistakes, if I have a number like any random number, then you know this is ones, tens, hundred, thousand. But this is tenth, this is hundredth, and this is thousandth, and so on, so forth. But here it's 1, 10, 100,000, but after decimal digit it's tenth, hundredth, thousandth. Okay, so we have been asked to round off this number, which is up to 3 decimal digits. We have to round it off to nearest tenth. Nearest tenth means up to first decimal digit. After decimal, only 1 digit we have to keep. So here if you round off 3, so this 8 will remain as it is because 3 is smaller than 5, and then when we round off 8, since it's more than 5, so this 5 will increase, and what I'll get is 0.6. So the correct answer is this, 0.6. If you guys have any doubt, then you can ask, because it's very important to get this clarified. Otherwise we'll continue with doing more questions now that hopefully will be able to clear your doubts also. Again we have one more round of question. This is, let me have some water. Okay. So in this question we have to round off, this is a number given, to nearest hundredth. As I told here that the first digit is tenth, second is hundredth, and so on. So here if we have to round it off to nearest hundredth, that means we have to go to, after decimal point we have to go to 2 digits. So let's see what it will become. Left side of decimal point will remain as it is, and when we'll see 4, this is smaller than 5, so it will not do any change to number 8. Then I'll see number 8, since it is more than 5, it will change this number 3 to 4. So 29.04 will be my final answer because I have to only round it off to 100th digit. If it would be, the question would be that round it off to 10th digit, then I will further round it off, and because it's 4 which is less than 5, so this would become 29.0. But since the question here is asking us to round it off to 2 decimal digit, so 29.04 is the correct answer here. Okay. Now these are the questions that I have taken from last year's assignment. So because I cannot solve this year's assignment, those you need to solve yourself. But here we will be practicing many so that you will know how to solve it for your this year's assignment. Okay. So the first question is this. I have also combined this time. Last time we talked about error analysis. So those questions also I am combining so that it will help you for your first week's assignment that is due, right? So yeah, this will be helpful. So the first question is based on calculating percentage error. The length of a cylinder was measured using vernier caliper several times. Following readings were obtained. These are those readings. Calculate percentage error. So last time we had seen the percentage error when we calculate for anything, like here length we are talking about. So when we want to calculate the percentage error, we denote it with this delta symbol. So percentage error in length will be the relative error, that is we'll take absolute error, its mean we'll take, and ratio with this mean. This also mean means average, right? We'll take average of all the absolute errors and average of all these lengths, and when its ratio is multiplied by 100 we get percentage error. So here we have to calculate these two quantities to find out this percentage error. So this experiment was carried out using this instrument many times. How many times? 1 2 3 4 5 6 and 7. Okay, so this experiment was done 7 times. So what is the mean length we get is will be average of all these values. From next onward we can do it quickly. Here just I want to show you all the steps so that you understand how it has to be done. Plus 1.16, these, like, the same thing is measured many times and these are the different values we are getting. So the mean length will be sum of all these measured values divided by number of times the experiment was done, which was 7. So when we will take mean, I'll use my calculator to see to calculate this. Yeah, this is 1.12 plus 1.11 plus 1.13 plus 1.10 plus 1.14 plus 1.15 plus 1.16. So sum I'm getting 7.91. Now this divided by 7 will give, this will give 1.13. Okay, now this 1.13 centimeters, this is the average length. Now we have to calculate this mean of absolute errors. Absolute errors, if you remember how we do it, for every value we have to subtract it from the mean value. So delta L1 means the mean minus the first value, which is 1.12. This will give 0.01. Same way, absolute error in second value, 1.13 minus 1.11, this will give 0.02. Absolute error in third measured value will be 1.13 minus 1.13. Okay, so this will be 0. Absolute error in fourth value will be 1.13 minus 1.10, that is 0.03. These all are in centimeter. Yeah. Absolute error in fifth value, it will be 1.13 minus, oh, also like this is positive, this is positive, this is also positive. Okay, anyway, while taking the mean we take the absolute of the values, so sign won't be a problem there, but just to, yeah, confirm again, fifth value is, yeah, 1.14. So here this value will be minus 0.01 centimeter. Absolute error in sixth value, this is 1.13 minus 1.15, which is 0.02 centimeter. And the absolute error in seventh digit or seventh value is 1.13 minus 1.16, which is equal to 0.03 centimeter. Now we have to take mean of all these absolute errors. So I'll have one more slide for this. So delta L mean, that I have to take all this 0.01, these are positive. When it becomes negative also, I have to take absolute of this. So the mean will be 0.01 plus 0.02 plus 0 plus 0.03, oh, and 0. I'll take absolute of this. Oh, this is also negative. This is also negative, but I have to take absolute of this. So it will be 0.01 absolute of this, absolute of this number, and absolute of this number. Taking absolute basically what means is we have to ignore this negative sign. So let's add this. So it will become 0.01 plus 0.02 plus 0 plus 0.03 plus 0.01 plus 0.02 plus 0.03. So sum of all these absolute errors will be 0. Mod of all these absolute errors, sorry, 0.12 divided by total 7. This will give us 0.017 centimeter. And this, if we round it off to 2 decimal digit, because we are, all these numbers were up to 2 decimal digits, so we'll round it off, and this will become 0.02 centimeter. So this is delta L mean. Now we have to find out percentage error in length. So again, the formula is this times 100. So this delta L mean, I got 0.02. L mean we had found up to 2 decimal digit, that was 1.13 centimeter. 1.13 centimeter. So final answer, let me see, 0.02 divided by 1.13. So again, if I am calculating with my calculator, it will give me 0.017699115. Maybe if you have a scientific calculator, it may give even more decimal digit. Right now I'm just using my phone's calculator. But so again it's giving these many decimal digit, but we have to keep in mind that we have to consider only till either if you go with this rule, then you have to consider only to the minimum number of significant figures. Here the minimum number of significant figure is 1. So you will round it off and it will become 0.0. Here if you start rounding it off, then you know this will become 7, because it will become 7, this will become 8. Since it will become 8, this will become 2, 0.02. So after rounding it off, because here you can see it has one significant figure, so putting the rule also, you will get 0.02, and then multiply it with 100, it will become 2%. So the relative error was 2%. So here you can see we have combined the concept of rounding off significant figure and the formula of error analysis. So this is how it has to be done. So I think this was in pretty much detail. Still, if you have any doubt, you guys can ask. And meanwhile, we will move to another similar question. Okay. So the next question is, the focal length of a convex lens was measured a number of times. The mean focal length was found to be mean focal length. Focal length we can represent by small f. So this is talking about an experiment where we are using a convex lens and we are doing some experiment. Here we are not talking about experiment, but it's given that we are doing some experiment and the focal length is measured many times, and what we are given here is the mean focal length. We did that experiment many times and mean focal length value we found is to be 10.41 centimeter. Now if the mean absolute error, if the mean of all the absolute error in the value of focal length is 0.13 centimeter, calculate the percentage error. Again, so percentage error in focal length value, the formula is this. Right? So we are already given these things, we don't need to calculate anything. We'll put in the formula 0.13 divided by 10.41. So again, using calculator, 0.13 divided by 10.41. What I'm getting is 0.0124. There are more digits that I'm seeing on my phone, but okay, I'm just writing this. Now again, using the rule of significant figure, we are dividing two numbers, and here number of significant figure is 2, here number of significant figure is 4, but we have to consider the number of significant figure the least one, right? So here it's only 2, so our final answer should also have only 2 significant figures. These two are anyway not significant, so up to here I have to round it off. Well, yeah, so let's round it off. So this will make it 9, it will become 9, this will become 5, this will be 5, but this is a even number, so it will remain 2. Sorry, I again forgot 100 here, we have to calculate percentage, right? So there will, this I hope you understood, you have to round it off up to 2 significant figure, because division that we are doing, one number has only 2 significant figures, so final answer will also have only 2 significant figures. Here these are not significant, only 1 and 2 are significant digits. So when we multiply it with 100, we will get 1.2%. So percentage error here is 1.2%. C is the correct answer. Okay. Now moving on to, so let me save it. It will be better. it's getting little hanged, but it's should be fine. Yeah. So yeah, let's do this next question. The length and width of a rectangular plate are this. So we are given length as 16.30 plus minus 0.05 centimeter. Okay, this should also be centimeter. They missed right here it seems. Okay, so we have been given the actual value and the error in it. How the error is coming, we do not need to think much about it, but this is the given value. So this is the value for length. Now the width is given to be 13.80 plus minus 0.05 centimeter. So up to 2 decimal digit, whatever equipment we are using to measure these lengths and widths, it's giving the value still 2 decimal digits. So this is how it is. We have to calculate area of the plate and find the uncertainty in the area, also means the error value we have to find it out. And further it's asking round off to two significant figures in the error of area and four significant figures in area. Okay, we will see this. So first we need to calculate area of plate. So we'll start with these actual values. So area of a rectangular item, we know its length times breadth. So this will be 16.30 times 13.80. What will this give is 16.30 times 13.80. Value I am getting is 224.94. And here four significant figures, here also four significant figures, so this should also be four significant figures. So I'll round it off and it will become 224.9, right? Here there are four significant figures. Even in question they had asked us to round off to error, we have to round off to two significant figure, and the area we have to round it off to four significant figure. And also with our knowledge of the rule for significant figures, we know that we are taking product of two numbers, and this number also has four significant figures. This 0 is significant, if you remember, it's coming after decimal digits, so this is significant. So this has four significant figure, this also has four significant figure. So final answer, although with calculator I am getting it like this, but I should report it like this with four significant figures. So my answer of area will be 224.9 centimeters square. Now further I need to calculate the uncertainty or the error in this area value. So for error, you know, relative error, relative error, you know, we find out like this, right? What we call absolute error in area divided by mean area. Or so how we'll do this, the formula of area is length times breadth. So relative error in this will be relative error in length, and which is given by delta L over L, plus relative error in width. Sorry, I am using W here, I should use W everywhere, right? So this is the rule. This we had discussed in last week's session. So what we'll get is relative error in area, it will be given by this delta L, the L is 0.05 and the actual value is 16.30, plus the error in width is 0.05 and actual width value is 13.80. So what will it become? 0.05 divided by 16.30. Okay, so this will become, and again I'll consider, okay, up to, I'm taking division, so I'll only consider my final answer. This is 0, should have one significant digit, so my final answer will be 0.00. I'm getting 3067, but I'll keep it up to only one significant figure. The same way, if I'll divide this 0.05, yeah, 0.05 divided by 13.80, so I'll get 0.00. I'm getting 36, so I'll round it off to first decimal digit. I mean, yeah, for one significant figure, so it will become 0.004. The last one, I hope I did correct. 0.05 divided by 16.30. Yeah, that was correct. This is up to only one significant figure. I am keeping these. So when I'll add, it will become 0.007. This is the relative error value. Now I have to find out the uncertainty. So that uncertainty means the error in area. This I found out relative error. Relative error is this. Now I have to find out this. Means whatever I got, I'll multiply it with this actual value of area. So 0.007 times area, which was this, 224.9. So it will give me 224.9 times 0.007. So the answer is 1.5743 is what I'm getting. I'll restrict it on to this much. Then I can write it as 1.6 also. I can write, I think. Anyways, it's 1.6 centimeter square. Then area of plate I can write finally with considering this error, 224.9 plus minus, because they have asked up to error in area up to two significant figures, so we have to give up to two significant figures. So the final answer should be 1.6. I don't know why they have kept 1.5. It should be 224.9 plus minus 1.6 centimeter square. If they are rounding it off at the end, maybe then they can get 1.5. Otherwise, if we are rounding it off at every step, maybe because of that there is little discrepancy, but yeah, I think it should be 1.6 centimeter square. Okay. Now the next value is, our next question is, sorry, the length, breadth and thickness of a rectangular sheet of a metal are, okay, so the length is 4.234 meters, breadth is 1.005 meters, and thickness is 2.01 centimeter. Give the area of the sheet, the correct significant figures. Area of sheet, oh, surface area I think they are talking about, because for area we only need length and breadth. I think if they are talking about surface area, then it means it's like a cuboid. The sheet is like a very thin cuboid, right? So surface area means 6 faces, the total area we'll calculate. So for that we need to first keep all these in same SI unit, right? These are in meters, so we'll change this also in meter because our final answer also is in meters. So I'll change this into meters, then it will become 2.01 centimeter. When we'll change to meter, it will be 10 to the power minus 2 meters, or 0.005 0.0201 meters it will become. So the formula for surface area is 2 times of length times breadth plus breadth times thickness plus length times thickness. So when you, okay, let's substitute these values. So length is 4.234 times 1.005 plus 1.005 times the thickness is 0.0201 plus 2, sorry, 0.0201 multiplied by 4.234. Okay, so then you will take product of all these and multiply it by 2. I think we have a lot of questions, so I'll try to solve this faster. When we'll take product and multiply with by 2 and rounding it off, it will give us 8.72 meters square. You can try this, and considering all the rules of error analysis and significant figures, you will get that the value is coming to be, I mean, there will be more decimal digits here, but you have to round it off up to 2 decimal digits or 3 significant figures. Okay. Yeah. So the answer is this 8.72 meters square. Let's go to next question. It is from error analysis again. A physical quantity P is related to 4 parameters A, B, C and D, and the relation between them is given by this. The percentage errors are, okay, so we have been given that percentage error in A is 1%, percentage error in B is 3%, percentage error in C is 4%, and percentage error in quantity D is 2%. Okay, what is the percentage error in the quantity P? Since quantity P depends on these values, the relation is given like this. So the percentage error in P, if you recall last week we had discussed these things, it will be like this: 3 times the percentage error in A plus 2 times percentage error in B, and all these denominators will again be added, plus half, it will be percentage error in C plus percentage error in D. So yeah, so basically this is 3, oh, it's already given, percentages are given, so this will be 1 plus 2, percentage error in B is 3, this will be 4, percentage error in D is 2%. So total will be 3 plus 6 plus 2 plus 2, that is 13%. If the value of P calculated using the above relation turns out to be 3.763, to what value should you round off the result? It's asking, first we have calculated this, then it's asking that if the value of P using above relation comes out to be this, up to what value should you round off the result? Since the percentage error is coming out to be 13%, that is, there are 2 significant figures. Okay, so this error also should have 2 significant figures. So when we'll round it off, it will become, when we'll round it off till here, it will be 3.8. So the correct answer should be this. The correct answer should be this, 13%, and this should round off to become 3.8. So A is the correct answer. Next question is, when the two resistance R1 and R2 are connected in series, Then calculate the value of percentage error of effective resistance after rounding it off. So here we have to connect these two resistors in series and find out effective resistance, that is total resistance. When two resistors are connected in series, this we had discussed in detail in experimental physics 1, that how this relation comes, but for this question we'll just take directly the total resistance when two resistors are connected in series is given by R1 plus R2. So here R1 R2 are given, so the total resistance will be 4.0 plus 9.1 ohm. This will be 13.1 ohm. Okay, decimal digit 1, so yeah, decimal digit up to 1. Now we have to give the error values also. So for error values, for error we have to calculate actually percentage error. Again, the percentage error in R means the percentage error in R1 plus the percentage error in R2. It will be, no, sorry, this is not percentage error, these are absolute errors. So if we have to, when it's given like this plus minus, then those are actually delta R1 delta R2, right? So the absolute error in total resistance is absolute error in R1 plus absolute error in R2, which is 0.1 plus 0.2 ohm, which is actually 0.3 ohm. So this is the absolute error. Now for percentage error in this total resistance, the percentage error will be the absolute error that we got divided by the total total resistance. So this we got 0.3 and this was 13.1 multiplied with 100. Oh sorry, I forget it every time. If we have to find out percentage, we have to multiply it by 100. So this will become, again using calculator for doing this calculation, get 0.3 divided by 13.1. This will be 0.0. From the calculator I am getting many decimals, but what we have to be careful here is significant figure 1, so significant figure here also should be up to 1, right? This will be 3, this will be 2, and multiply it by 100. So like this many, and further decimal digit I am getting in calculator, but I have to keep in mind that I have to finally write it like this, because significant figure should be 1. Or if it's asking round off to two significant figures, then okay, this is the rule. But if it's asking that we have to tell the answer with rounding off to two significant figures, then we have to round it off to two significant figures. Okay, then I'll keep here 3 also. For some reason it wants us to do that, so we have to do that. Otherwise, if there is nothing in specific asked, then we have to see that our by default rule that we have to take the least number of significant figure, which is 1 here. But here we have been asked to round off to two significant figure, so we'll round it off to two significant figure and then multiply it by 100, which will give us 2.3%. So while doing the problems, be careful what all the things we have been asked. So it's the similar case as if like we are doing some question with acceleration due to gravity, like g value we know. By default, if nothing is given, we have to take 9.8 meter per second square. Sometime it's given that you can take it as 10 meter per second square, that time we do that. So same way here, if no condition is given, we'll take the by default rule of number of significant figure. But if in the question we have been asked that take it up to 2 decimal digit or up to 2 significant figure or 3 significant figures, so we have to do accordingly. So that's how we get 2.3% for this problem. So this is the answer here. Next question, this is also on errors. In a experiment to determine acceleration due to gravity, again we were just talking about this g, at a place a stopwatch with resolution of 0.2 second was used and total time for a certain number of oscillation was measured as this. So total time is measured as 100.2 seconds. Okay, and the stopwatch that was used to measure this time, its resolution or least count is 0.2 second. That means the error value is 0.2 second actually. Okay, so if the percentage error in measuring the length of pendulum is 0.3%, percentage error in length is 0.3%, what is the percentage error in the value of g? We have to find out the percentage error in the value of g. Okay, so whenever we do this experiment of oscillation, from the derivation we know that g value we can calculate from oscillation experiment, and the relation between time period and this acceleration due to gravity is this. It's 4 pi square L by t square. T is the time period of oscillation, L is the length of the string of our simple pendulum. So this is the relation we know, and this we'll use to find out the relative error in G. If relative error in L is given and this is the time period we have calculated, this is the error in this time period, so we'll be able to find out the relative error in T, and then we'll calculate relative error in G. So relative error in G will be, from this formula we can see 4 pi square is a constant, so error in these values will be 0. So remaining variable is length and time period, and they are like this. So that means relative error in G will be relative error in L plus 2 times, because there is T is squared, that's why 2 times relative error in T. This will be simplified what we'll get. Then relative error in length is 0.3%. Okay, 2 times the relative error in time period. This will be 0.2 divided by 100.2. Okay, so this will be 0.3 plus 2 times, let's see what we'll get. This will be 0.2 divided by 100.2. This is 0.0. What I'm getting again, calculating this with the calculator, 0.0019996, and more digits are there. So here if I round it off to one significant figure, then it will become 0.002. Okay, and when I'll multiply this thing, I'm rounding it off to get one significant figure. So you can see here only this digit is significant. When I'll multiply with 2, 0.002 multiplied with 2 is 0.004 plus 0.3. It will become 0.30. I'm sorry, I made a mistake here. This is not this percentage error, right? This is already given in percent. This we had to change to percent. So this will be 100 multiplied with 100. So this will become 0.2. Sorry, 0.2 multiplied with 2 is 0.4 plus 0.3. this, I'm sorry, let me write here what happened. I had to multiply it with 100. This is only relative error, right? I need to multiply it with 100 to make it into percentage. So this number, I'm rounding it off to one significant figure, and then I have to multiply it with 100. So what I'll get is finally 0.3 plus 0.4, which will give us 0.7%. So the percentage error in G value is 0.7%. This is the correct answer. Now next question. Next question is radius of a circle is measured to be. So radius of circle value is reported like this. This is in meters. Calculate the area of the circle. Calculate the area of circle gives the rounded off to three significant figure in area and its error. Okay, so radius of circle is this. We need to calculate the area. If you recall, area occupied by a circle is given by pi times r square. Okay, so pi is 22 by 7. Radius, we'll take this 10.8 and its square. Let's see what we get. 10.8 times 10.8 multiplied by 22 divided by 7, we'll get 366. I'll round it off to 3 decimal digits because otherwise I'm getting 5, 8 and more this, but I'll round it off to 3 significant figures to get 366, 367 also, 367 meters square. Yeah, it should be rounded off to 367 according to calculation. It should always round it off to 367 meters square anyway. So this is the actual area value. Now what will be the error in it? So again we'll calculate the error. For calculating the error, the relative error in area, let's denote by A. The relative error will be, first I need to calculate delta. Okay, so it will be, pi is a constant, so this will be 2 delta r by r, which will be 2 times the error in r is 0.2 divided by the r value, which is 10.8. So this will be 2 times 0.2 divided by 10.8, which is 0.037. So delta A will be this value multiplied with A, which is 0.037 multiplied with area, we got 367 meters square. So delta A will be 0.37, so it will be 13.58 meters square. Now we have to calculate the area rounded off to 3 significant figure. It should be, we can clearly see, if we round it off, it should become 367 meters square. I don't know why they are taking it like up to 3 significant figure means only 3 digits we have to keep. It should be 367. I don't know why they are keeping it 366. And the error in area is 13.58, and we have to keep the error up to, error also we have to keep up to 3 significant figures. So 3 significant figures means right now this has 4 significant figures. So further I'll approximate, round it off up to 3 significant figures means it will become 13.6 meters square. Oh, maybe, wait, here it's given meter, then I think there's a mistake. Either all these should be in meter or maybe this should be in centimeter. There is a issue. Okay, if we ignore the units, then correct value is this. That means this is the correct answer. But it should be 367 plus minus 13.6 and meter square as per the question. It's in meters, so this answer should also be in meter square. Okay, but at least we learned the procedure. Next question is okay. So next question is, a body travels a distance of 13.8 plus minus 0.2 meters. Okay, so the distance is 13.8 plus minus 0.2 meters. In time, it traveled this much distance in 4 seconds, and the error is 0.3 seconds. The velocity of the body within error limit. So velocity we know, velocity is distance upon time. So this will be 13.8 divided by 4.0, and what we'll get from this is, let me calculate, 13.8 divided by 4.0 is 3.45 meters per second. But I think, let's see, we have to, if they have not asked anything, I think we can round it off to one significant figure actually. If we go, no, sorry, two significant figure, because this 4.0, this is significant. So we have to keep two significant figures. So I will round it off. This is 5 and this is a even number. So when I round it off, it will remain 3.4 meters per second. Okay. Now I have to find out the error in velocity also. So the relative error will be delta d by d, relative error in distance plus relative error in time. Now delta d is 0.2, d is 13.8 plus error in time is 0.3 divided by the value of time is 4.0. This will be 0.2 divided by 13.8, which is 0.01. We have to keep, I don't know, one, let's just keep up to 2 decimal digit for time being, and then this will be 0.3 divided by 4.0, which is 0.075. Now we have to find this delta v. So this delta v will be whatever we are getting here, let me add, plus 0.014, that is 0.089. So this 0.089 multiplied with v will give me the error in v. This is 0.089 multiplied with v we calculated to be 3.4. So I'll get multiplied by 3.4 is 0.3026. I think we can only stick to up to the original value has only one decimal digit. So here also we'll round it off, because our answers also, they have not specifically told us anything. So when we'll round it off only to first decimal digit, it will be 0.3 meters per second. So our correct answer here is 3.4 and the error is plus minus 0.3 meter per second. So this is the correct answer. Okay, next question. So as I told, in these first two It's basically about rounding off error analysis and significant figures. So these we'll thoroughly, if we'll understand, will be, I think, clear. So that's why last time maybe I thought the number of numerical problems were not sufficient. So this time mainly I'm focusing in this. And also, since we didn't have much experiment to understand in this week's lecture, so that's why like we can utilize this time to do more problems. So let's do this question. Here the radius given, radius of a sphere is, okay, radius of a sphere is 5.3, and there is some error in this value as well, and this is in centimeter. Percentage error in its volume, we need to calculate percentage error in volume. Now for a sphere, volume is given by 4 by 3 multiplied by pi multiplied by cube of the radius. So the percentage error in volume will be, this is a constant, pi is also constant, so this is the only variable we have. So this will be 3 times percentage error in radius. So 3 times, what is the percentage error in radius? 0.1 divided by 5.3 multiplied with 100. Yeah, let's not forget 100 here. So this will give, okay, 3 times 100 divided by 53. Okay, so final answer I'll get is 5. Oh, I have to not calculate, it seems. I have to just keep it as it is. So 3 times 0.1, yeah, we don't even need to calculate, we just have to keep it like this. So our answer will be B. Answer B is correct. We don't need to calculate. Next is, length of a cylinder is measured with a meter rod having least count of 0.1 centimeter. Its diameter is measured with vernier caliper having least count 0.01 centimeter. Given that length is 5 centimeter and radius is 2 centimeter, we need to calculate percentage error in volume. So this is a problem on cylinder. Its length is measured with meter rod having least count of 0.1 centimeter. Means its length value, given that length is 5 centimeter, so length is 5 centimeter and it's measured using equipment with least count of 0.1 centimeter, means the error in this value will be 0.1 centimeter. Okay, next is its radius. Its radius is measured to be 2.0 centimeter and the equipment used is vernier caliper whose least count is 0.01 centimeter. Okay, so its diameter is measured, okay, with least count 0.01 centimeter, means the least count in the radius will be, sorry, the error will be 0.01 centimeter. And the percentage error we have to calculate for the volume. Now what is the formula for volume of a cylinder? That is pi r square times L. Okay, so this implies the percentage error in volume will be, again pi is a constant, so we'll left with 2 times percentage error in radius plus percentage error in length. So the percentage error in volume will be 2 times the percentage error in radius, means 0.01 divided by 2.0 multiplied with 100 plus percentage error in L will be 0.1 divided by 5.0 multiplied with 100. We'll solve this and we'll get 0.01 divided by 200 to 0.0001 plus 0.1 divided by 5 multiplied by 100 is 2. See, is it correct? We just confirm 0.01 divided by 2 times 100, 0.5, okay, times 2, sorry, this is 1 and this is 0.1 divided by 5 multiplied by 100, this is 2, so total is 3%. So the percentage error in volume for this particular problem is 3%. Okay. Next question. You measure two quantities so we are measuring two quantities and the value okay, so one quantity is this, another quantity is this. We should report the value for this within the error limit. Okay, so it's same, like there is some parameter a and b and we have to multiply and take square root of that and we need to tell what will be this final value. Say this final value, let's call it something, let's call it p. I don't know what this exactly is, let's call it p. Okay, so to calculate this p, it is root of a times b, right? So what this value will be, a times b means 1.0 times 2.0, which is 2.0, so it will be root 2. Root 2 is actually approximately 1.414, and since all this is in meter, so a times b will be meter square and root of that will be meter again. So root 2 we are taking like this. Now we have to find out the error, that is delta p is what we need to find out, so that we can report the value like this, p plus minus delta p. This will be our final answer. We have found out p, okay, root 2 meters. We need to find out delta p. Now you know relative error is given like this, right? Here it's root, so it's half delta a by a plus delta b by b. Okay, now delta a is 0.2 and value a is 1, delta b is 0.2, b is 2, so this is half times, this will be 0.2, this will be 0.1, so this will be half times 0.3, it will be 0.3 divided by 2, 0.15, but we do not have to find out a relative error, we have to find out delta p. So delta p by p is 0.15, so delta p will be 0.15 multiplied by p. So this will be 0.15 multiplied by p, and p is this root 2, 1.414, right? So this will be 0.21, this will be some 0.21 meters. So if we round it off to one significant figure or one decimal digit, will be if we round it off, it's not given, but in the answers we can see that the values are only up to first decimal digit, so we'll round this also up to one decimal digit, okay, and the error also we'll round it off to one decimal digit, so it will become 0.2 meter. So A is the correct answer. Okay, so We read, I think, more than 10 questions we did based on all these things that we had discussed: error analysis, significant figures. Now, there were some lectures this week where the professor started introducing us to various components in that we see in an optics lab. Okay, so yeah, in the lectures he has talked about that whenever we are uh, going to carry out experiment in an optics lab, what are the conditions there should be, what are the components we should have there. Like mostly we see spectrum or we use light in optics, of course. So preferably many times we need a dark room to be able to see those spectrums, and we need optical bench to keep our optical components. There are various kind of mirrors: plane mirror, concave mirror, convex mirror that we use there. Similarly, concave and convex lenses that we use there. Then telescope with which we see, eyepiece, widescreen, pinhole, various kind of light sources, which includes some red or green light, laser light source, or in sodium light source, which is yellow in color, or incandescent light sources. So these are like basically this week he started giving us these basics of the components. But let's focus on one formula which tells us about emission spectra. What will be the wavelength of emission spectra? This is usually it comes from when we talk about hydrogen atom or similar atoms, atoms similar to hydrogen. This formula is called Rydberg formula. So what happens whenever an atom, its electron gets excited to higher state, like here we have an atom. These are its various shells, K, L, M, N. As you can see, yeah, N is equal to 1 represents K shell, this is L shell, this is M, N, and so on. So this is the orbital uh, position of atom, and if electron is excited due to any means, maybe some heat was given to it or some other thing, so if electron goes to higher quantum number, that is higher shell, and when it comes back, because it stays there only for some microseconds, after that it comes back, if it when it comes back, it gives off that differential energy in form of radiation, which this radiation has some wavelength. So to find out what is this wavelength, we have this formula called Rydberg formula. So what are the things here? There is one constant known as Rydberg constant. Its value is given by this. Lambda is the wavelength, Z is the atomic number of that atom, NL is the lower energy level, NH is the higher energy level. You can call it higher energy level or upper energy level. So what this formula tells is, if atom got excited due to any means to some higher energy level, if that higher energy level NH is anything, it could be anywhere, but if after ejecting radiation it comes to the lower level of 2, sorry, if 1, if it comes to 1, then the radiation it will eject will be part of Lyman series. If after giving out radiation it's coming down to lower energy level of 2, that is this L shell, then whatever wavelength it's giving out, that will be part of this Balmer series, and similarly Paschen series, and there further which is called Fun series. So this is what gives us spectra, and these are the various series. But to find out what will be the wavelength of that light depending on the higher energy level and lower energy level, this is the formula we can use to find out that wavelength. So this is called Rydberg formula, which is, as you can understand, it's very important to understand to find out the wavelength of that light. Now let's do questions based on this thing that we have understood. So the question is, when electrons jump from n is equal to 4 level to n is equal to 2 level, angular momentum of electron changes by. So it's saying there is an electron, it jumps from n is equal to 4 level, there is n is equal to 3, n is equal to 2, n is equal to 1, the lowermost. Okay, so there is an electron that jumps from fourth energy level to second energy level. Then what will be the change in its angular momentum? If you recall, this was given by Niels Bohr, that electron moves or revolves around the nucleus in an atom in discrete orbits, right? And in also its angular momenta is uh, integral multiple of h bar. So it's not like continuous energy is not there. There are discrete energy level represented by this principal quantum numbers, and the angular momenta is integral multiple of this h bar. So if the electron is at n is equal to 4 level, then its angular momentum will be, let's denote it as L4, its angular momentum will be nh bar, means 4h bar. When this electron is at n is equal to 2 level, its angular momentum will be 2h bar. Okay, now we have to calculate the difference of these two angular momentum. So difference in the angular momenta will be L4 minus L2, that is 4h bar minus 2h bar, which is 2h bar. Here the values are in h over 2 pi, so you know h bar is h over 2 pi. So this will give us h over pi. So this is the change in angular momentum if the electron is coming from fourth level to second level. So h over pi. This is the correct answer. This is the next question. Wavelength of two different waves are, okay, one is 6000 angstroms, another is 5000 angstroms. Find out the difference of their wave number. Okay, wavelengths are given, we need to find out difference in their wave number. So if you recall the relation between wavelength and wave number, so wave number is given by 1 over wavelength. Okay, this is the relation between wavelength and wave number. So for this lambda 1 wave, the wave number, let's denote as with subscript 1. Corresponding to lambda 1, the wave number will be 1 over 6000 angstrom. Since answers are in meters, so we'll change it into meters. It will be 6000. 1 angstrom is 10 to the power minus 10 meters. Okay, so this wave number of first wave will be this will be 1 divided by 6000. This will be 0.000167 and 10 to the power 10 meter inverse, or I'll write this as 1.67, or wait, 1 2 3 4 5, okay, 1.67 10 to the power 6 meter inverse. Okay, now wave number for second wave, it will be 1 over lambda 2, which will be 1 over 5000 angstrom. 1 over 5000 angstrom means again 1 over 5000 times 10 to the power minus 10 meters. This will be 1 divided by 5000 is 0.0142, and this will become 10 to the power 10, and this will become meter inverse. Again, up to taking it to exponential, like for, I mean, the scientific way of writing is this 1.42. This is correct, right? 1 divided by, let me just see, 1 divided by, wait, what happened? 1 divided by 5, 1 divided by 5000 is 0.00, I'm sorry, it is 0.0002, and then this, so it will be 4, it will be 2 10 to the power 6 meter inverse. Yeah, so when we have to take difference of these wave numbers, means first wave number minus second wave number, so we'll get, or okay, we'll take second and then first, because negative doesn't make any sense. So it will be 2.0 minus 1.67 multiplied by 10 to the power 6 meter inverse. This will give us 2 minus 1.67. This will be 3.3 10 to the power minus 6. Sorry. This is, so wait. Okay, just write this. Okay. Yeah. So when I'll subtract this, I'll get 0.33 10 to the power 6 meter inverse. Now our answers are in 10 to the power 5, so when I'll change it to 10 to the power 5, I'll get 3.3 10 to the power 5 meter inverse. So answer is not matching, it should be this. I think one reason could be the approximation, because I was getting 1, 6 and there were a lot of 6s. I have rounded off, maybe they did not. If they'll consider 1.66, then it will be 0.34, and then the answer will be 3.4. Anyway, if we have done it correctly, it should be 1.67, and with that, if you are getting 3.3, then you can see the closest value is this. So this should be, you can mark the correct answer. Okay, one more question we have on this. This is the longest wavelength in the Lyman series for hydrogen is this. If you recall, Lyman series was when the upper level, I'll again show the diagram, the electron, when it's come from higher level to lower level, n is equal to 1, then it could, if it's coming from second level to first level, or it's coming from third level to first level, or it's coming from any level to first level. If it's coming to first level, then whatever radiation it will emit, it will make Lyman series. Okay, so the lower level is 1. If it's a Lyman series, means the lower level is 1. So here the question is about Lyman series, means one thing is clear, that the lower level is 1. Okay, so they are talking about hydrogen atom, means Z is equal to 1, right? Atomic number is 1 for hydrogen. So longest wavelength is this. Calculate the Rydberg constant. So what was the Rydberg formula? Here we had seen, right? This you can, the Rydberg formula says then 1 over lambda is Rydberg constant, square of atomic number multiplied with 1 over the lower level square minus 1 over the upper level or the higher level, you can call it anything. Okay, now They're talking about longest wavelength. Again, looking at this, if the energy difference is more, I mean, if it's coming from very high energy level to first level, that means the energy difference is more. And since you know wavelength is inversely proportional to energy, means if energy difference is more, that means the wavelength will be very less. So here if you are talking about longest wavelength, then energy will be the minimum. And when will the energy be minimum? When it's jumping from second level to first level, then energy difference is minimum in this situation, right? When electron is coming from second level to first level, then energy difference is minimum and the wavelength that goes out will be maximum for Lyman series. Okay, that means this longest wavelength condition tells us that the upper uh, level is 2 and lower level is 1. Atomic number also we know because it's hydrogen, so atomic number is 1. Wavelength we know 1215 angstrom. Now we have to find out the value of R. So substituting everything, lambda is 1215 angstrom. Answer is in angstrom, so I'll let it be in angstrom only. R we have to find out, Z is 1 and lower level is 1, right? Square of 1 is 1 and square of 2 is 4. So this will be 4 minus 1, 3, 3 by 4, 3 by 4. So R will be 4 by 3, okay, and 1 over 1215. I have taken this 3 by 4 on the left side, so it became 4 by 3. Now let's calculate this. 4 divided 4 divided by 3 divided by 1215 is 0.001097 angstrom inverse. Okay, if I'll change it into some power, it will be 1.097 times 10 to the power minus 3 angstrom inverse. So the correct answer is answer A. So this is the correct answer. So yeah, so these were the problems that we did based on, again I'm repeating, error analysis, significant figure, rounding off, which were very important. Further we won't be able to focus on these things. Yeah, okay. So and then we also did this few questions based on atomic energy levels and Rydberg formula. I hope all this is clear. If there is any question, you guys can ask, or it's already been 5 o'clock, we can end this lecture and we'll meet next week after uh, the next week's lecture are released. We'll watch that and we'll be discussing questions based on that. So if there is any question, you guys can ask. Otherwise, we can end today's session. Do you guys have any question? If not, then okay. Thank you for joining. We'll meet. And of course, I'll be uploading all these videos and this presentation also on the Google Drive. I hope you are able to access that. And that NCRT unit chapter also I'll upload on the Google Drive for units and for the chapter name is unit and measurement. That is useful for understanding the significant figure rules and error analysis. So I think that will be helpful. Okay then, let's end today's session. Thank you.